طيب بسم الله الرحمن الرحيم. So we talked last time about the IP address version 6 configuration. So we talked about 3 different methods for providing the IP address configuration for IP version 6. We talked about the Slack method and the AUI 64, which is performed by each interface to assign itself an interface ID based on the physical address. And also we talked about the use of DHCP version 6 to obtain the complete IP address configuration, including the full IP address version 6 and the DNS information. So today we want to discuss the last topic of chapter 8, which is to test connectivity. So for testing connectivity, we use a protocol as part of IP version 4, which is called Icmp. So like all other protocol suite for IP, so there is Icmp version 4, and there is IP version 6. So for IP version 4, simply we have only two messages that are used to test connectivity. So we have what we call echo request and echo reply. So these are network layer messages as part of Icmp, right? And these are used for testing connectivity. So in order to trigger these messages in the network layer, we have some application level commands. So we perform application level command, which are very common to test connectivity. One is what we call ping. So ping is used to test connectivity. So we just say ping and IP version 4 address. That's the format. When we do this, the Icmp will trigger the echo request message to be sent, and this IP address is the IP address of the destination. So for example, if this node wants to test connectivity with this node, for example, so on this node we should perform a command called ping, and then we specify 10.0.1.1 as the destination address. Okay, so that's simply what is used as part of Icmp version 4. So in the echo reply, as part of the echo reply, so we can get some feedback or some result. So this result could be either host confirmation. So by host confirmation, we mean that this host will reply back with an echo reply saying that everything is good, and yes, I'm here, and you have connectivity with me, so we can talk, right? Of course, you can say ping localhost or ping 127, in which case we can, what we try to do here is to test the TCP/IP stack, because this is the localhost IP address. Another outcome of this is a host or network unreachable. Okay, that's the error by outcome. So if you try to ping a specific destination and you get an error message that says host or network unreachable, then you know that you don't have connectivity with this final destination. Okay. You can, which means that you can test connectivity with a host, or you can test connectivity with a network. Okay. So if we want to test connectivity with a full network, like this one, if we want from this host to test connectivity with this network, okay, what do? So we don't want to test connectivity with a specific host. We want to test connectivity with the entire network. What do? Ping which gateway? This one or this one? Yeah, F0, right. So this network is represented by this gateway, right? So That's exactly right. So if we want to test connectivity with the local network, if this host wants to test connectivity with the local network, then we ping this gateway, F1. If we want to test connectivity with a remote network, then we should ping gateway. What we should never do is to ping a network address. Okay? Network address is not a valid destination, as we said before. Okay, so keep this in mind. Huh? I don't want anyone to say ping network. Network address is not an address that refers to a destination that contains a network, right? So if we want to test connectivity with a network, then we have to use the gateway address. So that's very important. Type. Number three, which is a very special outcome, we call it time exceeded. Okay, so what does that mean?
Time to live equals 0.
Okay, so this means that the field which is time to live equals to 0. This time to live is part of the IP version 4 header, right? So what happens is that when we send any packet, we set the time to live to a specific number, right? Usually by default, the operating system assigns a TTL. TTL usually equals to 255. If you don't specify any number yet, the default is 255, which means that this IP packet will go through 255 hubs or routers. After this, it should be discarded, destroyed. Okay, so the TTL is used as part of the echo reply to indicate that the time has exceeded, which means that this packet has not reached to the final destination that you want, and in that case, I'm going to have to discard it. When we discard the packet, we send back an echo reply. So this particular error message is used as part of another command, which is also supported in IP version 4, which is what we call a trace route. اوكي واضح ان هم الاثنين بس اللي شافوا الفيديو الباقيين ما فيش خالص. اوكي so trace route is a command as part of Icmp version 4, which is usually used to not only to test connectivity with the final destination, but also to trace the probable route to the final destination. Okay, so if you have a host, this is a host, okay, and this host sends to a final destination. Okay, this final destination might be a few hops away. So, for example, you want to test a server, we want to test the connectivity with a server in China. Okay, so you use ping. What if you want to know all the hops that will get you to that server in China? So that you want to trace where does the communication stop. So at some point, okay, maybe you will get an error, in which case you want to know what is that hop that stops the communication or suspend the communication, so your communication does not go to the final destination. So first you try ping, and ping does not have any reply, no response. So you try trace route to see where the communication exactly stops. So what trace route does is very interesting. So between the host and the destination, there could be many routers, right, to the final destination. So what trace route does is that it sends an echo request, okay, with a TTL initially 1. Okay, I'll give you the bonus at the end, obviously. So TTL equals to 1. So what that means is this echo request will get stopped here by this router, and then this router will decrement TTL, so it becomes 0. So what will this router send back? Time exceeded, right? So when this host receives the time exceeded reply, this reply will have many information. One of them is the IP address of this gateway, which is what I want. And also some numbers to indicate the delay for the round trip time and so on. So you get rich information in terms of how much time does it take you to reach to that router. Okay? So in that case, the echo reply will stop at this point. Okay? Then we send another echo request with TTL, this time equals to 2, which means that this echo request will stop at the second hop, right? And then we get time exceeded. And we keep doing this until we get a feedback that's not time exceeded. Okay? Either by a confirmation or some kind of error. So in that case, you know exactly all the hops that this packet will go through, and all the delays related to how much time does it take to do a full round trip, okay, and all this information, which is used. So why do I say that? Why do I say trace route gives you some information about the probable route? Okay, so I keep saying probable route. Okay, why can't I say, the route, or the actual route, or the permanent route?
Because I don't know how many routes.
Hmm?
I don't know how many routes.
How many hops?
Routes will travel from the packet traveling from to.
Or the packet can go to different routes?
Because of the network layer.
يعني, let him answer. The packet can go to different routes?
No.
Huh?
Yes.
Yes. Why? Why? Because IP version 4 is connectionless. We said that at the very beginning. Okay? So when you send a packet to a particular destination, we cannot guarantee that this packet will go to the same route every time. So if you send group of cars to QU, we cannot guarantee they will go through the same route because we don't have any connection. That's why we say the probable route. Because in fact, maybe when you send many echo replies, they will go to different routes. We cannot guarantee the permanent route. ماشي كده؟ طيب. So that's the trace route. With this, this activity is.
If I remember, in IPv4 we have metric. Right?
We have what?
Metric.
Yes, the metric as part of the route. This is as part of the routing table. Has nothing to do with ICMP or the packet or the destination or echo request and echo reply. This is only in the routing table. Okay. So any question about ICMP version 4? So let's just do this activity and then we'll go to ICMP version 6. Okay. Okay, so if host 10.0.0.1, this one, wants to check TCP IP stack. So what is the command? Ping. And 127.0.0.1. Anything. It has to be a host address, huh? You cannot say 127.0.0.0. That's not a host address. It has to be a host address. Okay. Host 10.0.02, which is in that case this one. Okay, wants to check the communication to local network. So in that case, we should ping the default gateway, which is in that case F1. F1 here has the address has this network اللي هي 10.0.0.254. So it's 10.0.0.254. Okay. Host بقى 10.0.1.1 wants to test connectivity with the network 10.0.0.0. Okay. 10.0.0.0 is this one right here. So this host wants to test connectivity to the remote network. Okay? So we have to say ping, and what is the address back? Same. It's 10.0.0.254. Right? But this time, the difference between this and this is that this command this time is run here. So you should run this command from here as opposed to from here. Type 10.0.0.2 wants to check connectivity to local printer. 10.0.0.2 wants to test connectivity with the local printer. So in that case, it's again ping and 10.0.0.253, which is this address. Okay? Type host 10.0.0.1 wants to check probable route to host 10.0.1.1. So in that case, that's a trace route. And the IP address is 10.0.1.1. So not only that, you get one line to tell you host confirmation, but you get multiple lines. Each line corresponds to the routers that this packet will go through. So this activity is easy. So now we want to discuss no activity actually for this. We want to discuss a Icmp version 6. Okay, so Icmp version 6 as part of IP version 6 is much more complicated. So in addition to echo request and echo reply, which are also used, so you can say ping and IP version 6 address. That's given. So in addition to these, we have another two categories of messages. Two categories of messages that we have discussed them before actually, but we need to. We did not discuss the fact that these messages are part of Icmp version 6. Okay, so we talked about these messages, but we did not say that they are part of Icmp version 6. So what are these messages about?
Route A solicitation.
Router, advertisement and solicitation. And neighbor, advertisement and solicitation. Okay. So route, advertisement, it's actually route, not route. Route, advertisement, and solicitation, we talked about them before. We talked about them last lecture, which are used for IP configuration. Okay, we talked about them last lecture. So we said that if you have a router and this LAN has many hosts. Okay, so one of the ways to configure IP version 6 addresses to these hosts is the Slack method, right? So we said that the router may in fact send route advertisement message, which in that case uses what type of address? What type of address is used as part of a route advertisement? There's no broadcast in IPv6. It's called all-node multicast. And the address specifically is we talked about it. The address is FF02::1. Okay? So this route advertisement will send all the common information for the IP address configuration, which is the prefix. It will send, of course, the prefix, and of course the length, prefix length, which is typically 64. And ايه بقى تاني؟
the ID mask, the interface?
Sorry?
The ID interface?
No, the interface address gets assigned through the Slack method. Okay? And the gateway address. Sorry, here. Okay? Because the gateway address is also common. What we don't send as part of this message is the interface ID, because the interface ID is specific for the nodes. And then these nodes will individually use EUI64 to assign to themselves some address. So this is what we refer to as route advertisement, which is part of Icmp version 6. So now we know that this message is part of Icmp version 6. Type. So what about the route solicitation? What happens is that this message gets sent by the router periodically, and it may take like up to 40 seconds or a minute to get sent. Okay? So when a host first starts, it has the option, right? So one option is to say, I'm gonna wait for a minute, not be able to communicate to the internet until I receive the route advertisement, right? The second choice is to say, okay, so let me try to get to DHCP version 6 server to try to get a full IP address, okay? Or it may, in fact, so the router, in that case, so the router may, in fact, send route solicitation message, okay? So the router may send route solicitation message to trigger the route advertisement off cycle, okay? So the route advertisement is sent periodically, or if it's solicited, or if it's triggered by one of the hosts, okay? طيب, what is بقى the address that is used as part of route solicitation? لا يقول لي دي بصراحة, he deserves a special bonus يعني.
هو
FFEF, we didn't talk about this.
I'm going to guess
FF02 colon 2, right? This is all route multicast. All router multicast, right? So we said that we have two addresses. We have all nodes multicast, okay, which means that this message will be received by all the nodes on the LAN, or all router multicast, which means that this message will be received by all the routers. And this LAN, by the way, may be connected to multiple routers, right? One LAN can be connected to multiple routers. One of them has to be designated as a gateway, but all routers can. What's your name back? Kishore. Okay. So we have Kishore, and we have Hani, right? We have Nasir. Okay. So those are the ones who actually watched the video. طيب. So that's the route advertisement and solicitation. There is neighbor advertisement and solicitation. Neighbor advertisement and solicitation is used for a different purpose. It's not used for IP address configuration. It's used for they use multicast address. Yani, you are right. But what is the main purpose of the neighbor advertisement and solicitation? Which is what we call يا ناصر? Address resolution. Okay? طيب, هو مش address resolution has a specific protocol that we talked about before, which is ARP, right? Address resolution protocol. So IP version 4 used to use address resolution protocol, right? To send a broadcast message to ask about the physical address of a specific node. So if I want to communicate with a node, I know the IP address of this node. I want to know the physical address. As we said before, if that node exists on the same LAN, then we will have the same network mask. And in that case, I need to know the physical address of this node on the LAN. If that node exists in another remote network, then we do not share the network mask, which means obviously it's on a remote network. In that case, we need to know the physical address of the gateway. Bravo. Okay? So these, this ARP uses broadcast messages, and that's not supported in IP as version 6. So instead, IP version 6 incorporated the address resolution as part of ICMP version 6. So ARP for IPv6 does not exist. So ARP is only used for IP version 4. We cannot send ARP message with IPv6 address. We cannot do that. Okay? So instead, we have to use neighbor advertisement and solicitation. Okay? So if a node wants to know the physical address of a specific IP address version 6 node, then it sends what we call a neighbor solicitation. It solicits the physical address for a particular IP address, version 6. Typically, this neighbor solicitation uses solicited multicast address. Remember we talked about solicited multicast address, where we have a specific prefix /104, and then we take the last 24 bits of the global unicast, and then we concatenate it with the solicited multicast prefix, and then we send the packet with that solicited multicast address. Which means potentially that this packet for solicited multicast may in fact reach to more than one node. Because we said that solicited multicast may in fact target more than one node, right? Which means that I may in fact get neighbor advertisement from more than one node, not one node, okay? In general, okay? طيب, last thing بقى, can I actually send a neighbor solicitation with my own IP address, IPv6 address? Does that make sense? So I want to know if there is a node that has a physical address, okay, for my IP address. Doesn't make sense, right? In fact, here it does. Here in IPv6, it does. And it's used for a specific usage, which is called duplicate address detection. Okay? Duplicate address detection. So I want to know if there is another node on the LAN that uses my IP address, which happens typically when you try to configure IP address manually on a host without knowing that another node on the LAN may have the same address. If you have two nodes with the same IP address on the LAN, they cannot communicate. So one of them has to be disconnected completely, because we said that IP has to be, even private IP addresses on the same LAN, you cannot use the same private IP address. Okay, so neighbor solicitation can be used to detect the duplicate address. Okay, by sending a neighbor solicitation with my own IP address version 6. In that case, we try to detect the duplicate nodes with the same IP address like mine. واضح كده؟ So as you can see, ICMP version 6 is rather complicated. So it's used for 3 different purposes. One for testing connectivity using echo reply and echo request, and another usage for IP address configuration using route advertisement and solicitation, and another usage for address resolution, which is using neighbor advertisement and solicitation. Okay? Any questions? Mhm.
But why did they combine it? Like,
Why are they combined in ICMP version 6? Well, based on the need. So the standard for ICMP version 6, it included the connectivity using echo request and echo reply for backward compatibility. But they found that for IPv6, we need other things. So we need other usages. So either you incorporate this as part of ICMP version 6, or you incorporate it as part of any other standard. So for IP address version 6, there is no other standards because they are not relevant. These usages are not relevant, for example, for dynamic routing protocols. Because for dynamic routing protocols, they are used for routing. But this is not for routing, okay? So that's why the standard developers, they prefer to incorporate or integrate the IP address configuration and the address resolution as part of ICMP version 6. And it also makes sense to group some of these usages because of the lessons learned from IPv4. Okay? So they thought there is no particular reason to have ARP v6. Because ARP v6, ARP ARP in general uses broadcast messages. So we don't have broadcast messages as part of IPv6. Okay, so we'll give a quick introduction, which is what I'm trying to look for. Yes, this one. Okay, so we'll give a quick introduction about subnetting. So this is chapter 9. So subnetting is basically the concept of dividing our big network, like enterprise network or ISP, Internet Service Provider Network, right? It's a big network, right? We divide it into subnets, right? We divide it into smaller parts, okay? So this chapter focuses on this concept of subnetting. So first, by subnetting, we mean that, as we said before, the IP address, either IP address version 4 or version 6, it has like network address, and it has the host part, or interface ID in the case of IPv6, right? So by subnetting, we mean that we will add something in between here. We call it subnet number. Okay? Subnet number. Okay? Why do we need to do this? Why do you think we need to subdivide our big network into subnets and maintain like a subnetwork number and subnet mask? So starting from this chapter, we will not refer to network mask. We refer to subnetwork mask. Okay? Subnet mask. Why do we need to divide our big network into smaller subnets? Hadar?
make it less complex. Like
Actually, I can argue it's the reverse. So if I have one network, it's easier to manage. If I have multiple subnets, it's maybe more complex to manage.
for privacy.
How?
If there's one subnet and there's one router, and then the router can be configured to block certain kind, like you said, do back can be blocked. Then ping to a local is usually sent back. That's
Okay. Is that by guessing or you have read it? You guessed? I like your honesty. Okay, but your guessing is right. So let's talk about the motivation behind subnetting. Okay, so if we think about the situation at QU here, okay, at QU we have many LANs. Like we have a switch, okay, which covers, for example, the CS lab. Okay, which is composed of typically a switch, okay, and multiple hosts connected to it, okay? And we have another LAN, maybe EE lab, okay? Again, it has some hosts, right, connected to a switch. And we have another one for, like for example, finance office, okay? Again, same thing, okay? And then, as an enterprise like QU, we have a gateway router that connects us to the ISP router, right? The Uridu. So the question is, how can we design the network in between? So we have labs, and we have a gateway, right? So how can we design the network in between? So one choice could be that, okay, so I'm gonna make my design flat. I'm gonna have a flat design. By flat design, we mean that we will have a big, huge LAN, which means, okay, I'm gonna connect these using a switch. I'm gonna connect this and this maybe using another switch, and then connect the both to one switch, and then connect the switch to the router. What I have essentially done here is that I made the entire QU enterprise network as one big LAN, huge LAN, right? Because we said that LAN is terminated by router port, right? So as long as I'm using switches or hubs inside, it's actually making my LAN bigger and bigger and bigger and bigger, okay? So what happens typically is that the ISP, like Uridu, ISP assigns a range of IP addresses to QU, okay? And give this range of IP addresses to QU, and then QU will have control to assign these IP addresses to the hosts inside the LAN. So let's say that this range of IP addresses is like 170.16.0.0/16, which means that Uridu will say, okay, so take this specific network address and do whatever you want to do with it, okay? So you have 2 to the power 16 minus 2 host addresses you can assign, right? Typically, okay? So if I select this flat design, then essentially what I did is that I can use this range of IP addresses as one unit, okay? I use this range of IP addresses as one unit, which means that I can have 2 to the power 16 minus 2. It's one big LAN, huge LAN, okay? So what is the advantages and disadvantages of this? So in terms of advantages, this flat design will allow me to use address range as one big unit. Okay, so I will use this address as one unit, which means that essentially I can have up to 2 to the power 16 minus 2 hosts, because it's one LAN, right? But what is the disadvantage? The disadvantage now is that since it's one LAN, imagine if this node sends a broadcast message, okay? So what we'll essentially do here is that this broadcast message will find its way through the entire university, okay? So it will go through the entire. So what are the examples of broadcast messages? We send ARP, we send address resolution using IPv6. We have many protocols that provide broadcast messages, okay? So this flat design forms very large broadcast domains, okay? Like what is wrong with this, or what is bad about this? It's an overhead. So why does this node have to process broadcast message coming from this node, okay? So the second thing is what Kishore has mentioned here. It has to do with the fact that since this is a one big LAN, there is no isolation or privacy. So if one node here is compromised, okay, the traffic going from this node will reach all other nodes. So all the nodes inside the university can be infected, okay, by the compromises of one node. So here, there is no network isolation. Okay? So there is no isolation between the labs or between the small parts of the network, because it's one big network. Okay? So this is the first design. The second design is using the subnetting. Using the subnetting, instead of using these switches, I'm going to use routers. And then connect these routers with the gateway. So if I do this, routers are more intelligent and they can block all the broadcast traffic. So broadcast traffic that uses a frame physical address of all Fs will typically be blocked by the routers, okay? Creating some kind of isolation. So all these two issues have been fixed, because now I can make the broadcast domains smaller, okay? I can now have some isolation between the networks. So if one node is is compromised, this network is isolated and it cannot affect all other networks, right? Type. But what is the disadvantage here? The only disadvantage is that now I have to subdivide this big range into smaller ranges. So instead of having 170.16.0.0/16, okay, the network analyst or the network planner will divide this into 170.16. Maybe anything/24. Okay. So in that case, from 16 I went to 24, which means that this byte will be used as the subnet number. Okay? So in that case, I will assign, for example, this node to be subnet number 0. This node will be subnet number 1. This node will be, LAN will be subnet number 3. This will be 4. This will be 5. This will be 6, and so on. Okay? So I will divide this range of IP address into subdivisions. Okay? By doing these subdivisions, essentially what I did now is that from 16 going to 24, now each subnet will have to have hosts of 2 to the power 8 minus 2. Okay? So I can have up to 2 to the power 8 minus 2 hosts inside each of these subnets. Okay? So instead of losing 2 addresses for the big LAN, now I have to lose 2 addresses for each subnet. This is the only disadvantage for subnetting, okay? Because I have to subdivide the big range into smaller ranges. So that's essentially the motivation behind subnets, is to create some kind of isolation and smaller broadcast domains, because it's not efficient to have one huge, big broadcast domain for each enterprise. That doesn't make any sense, okay? So, but the cost that I had to pay here is I have to lose 2 addresses for each subnet now. So the entire chapter discusses how can we plan this subnet. Okay? Throughout this chapter, we will talk about how we can plan this subnetting. Okay? So our job is the job of the network planner, who can efficiently subdivide the big network into smaller subnets. How do we do this in such a way that makes it efficient? So that's what we will discuss in this chapter. Any questions? So that's brief introduction, and then starting next time we will dive into rigorous calculations But I wanted this big picture to be in your mind. Why do we do this? Because as part of the calculations, you will ask yourself, why are we suffering throughout these calculations? That's because of this big picture. Huh? So keep